So our second speaker today is Alex Netterville from Synopsys. He's a senior staff applications engineer. The title of his talk is Assertion IP for cache coherency and verification. He's working within the VC formal team at Synopsys. He has responsibility for various assertion IP products at Synopsys and has also undertaken consulting projects with large customers. He's based in the UK in Derby. Over to you. Thanks, Alex.
Great, thanks, Mike. Yeah, so I've got a little bit of a different pace here today. I'm going to start by describing, actually, I'm going to go quite basic, to be honest, and talk about sort of where we've kind of started from and with regards to the needs for coherency to exist in a system. And then I'm going to go on and describe some of our assertion IP products and look at some usage scenarios. Okay, so yeah, so I will describe the problem. Got a little bit of an animated set of slides there. And then I'm going to talk about a cache coherency protocol as well that addresses some of the issues in the scenarios that we're going to look at, and describe, as I mentioned, the assertion IP products that we have at Synopsys. I don't know if I'm going to consume the full 20 minutes, Mike. I hope that's not a problem, but we can certainly see what time is I wind up with. So here's a system with a single agent cache. And no coherency is really needed here, but really this system will stay coherent because there's only one processor, one main agent here, and it's the only observer of the data that it generates. It can cache data for performance reasons, for low latency, as can the interconnect. And this generally works fine. So why don't we just take a look at a couple of basic scenarios so that those that aren't familiar with cache hierarchies and kind of how they work can get a feel for what transactions look like in the system. So here's processor 0, and I'm going to give, first of all, a case where there's a read, and then I'll give you a case where there's a write, and we'll talk about sort of how writes allocate cache lines, etc. So first of all, let's look at a read in this processor. So the processor will look up in its caches, and it will say, okay, is that entry in my cache? And in this case, the answer is no. The cache doesn't have the entry. So what this core has to do is ask the interconnect for it. This interconnect will look up in its cache and see, oh dear, I don't have that data either, and make a read request to the memory. So the memory is kind of the outer part. It's not really a cache. It's kind of the canonical last resting place for where data is stored. And that memory will then return that piece of data to the interconnect, which will then, of course, cache it, and it will locally be available there to processor 0. And finally, it will return that data to processor 0, which will then cache it in its caches. So that's kind of the round trip. People have probably seen it before, but I think it's good to just look at this. So now I'm going to show you the case where there is a write in this system. Let's take a look. So processor 0 tries to write into this cache, and it sees that the cache line is not present in that cache. So this core in this case has a read allocate cache, so it has to it's required to go and perform a read to the interconnect. Of course, the interconnect in this case thankfully has the data, and in order to satisfy the allocation into that cache, it's going to obviously provide the line, which then becomes allocated. And in this world, in the world of caches, this cache line is now considered to be dirty or modified, depending on the protocol you'd be talking about. But in this case, of course, there is no protocol, but this data is now modified. And if you consider a weakly ordered memory model, this data here could sit in this cache probably for as long as it wants. And there's no real need for this processor to push that that data out to the interconnect caches or out to the memory, unless it wants to evict that line, in which case it would then, of course, push that data out to the interconnect. And then it's, of course, the interconnect's decision as to what it would do post that. But the fact that data can linger around in weakly ordered memory systems means that for coherency purposes, in a non-coherent system, it might not be possible to know where the latest version of a piece of data actually is sitting. So in order to kind of investigate that, why don't we look at a system where there's an interconnect, but this time there's two processors with caches. Again, this is a non-coherent system. There's an interconnect that also has a cache, and there's the usual memory sitting underneath it. So what would happen if in processor 0 and processor 1, you were to make simultaneous accesses, and one of those would be a read and one of those would be a write? So let's take a look at that. So they make their requests practically at the same clock cycle. They both then see, okay, we don't have a copy of this data, and this will be, I guess, the first time that maybe this has been accessed at all in the system, and both just happen to want this data at the same time. So P0 requires to do a read, as does P1, because this will be a read allocate cache. So they read the entry, they each perform a read to the interconnect. Now at this point, the interconnect needs to make an arbitration decision about how it's going to address these transactions. So let's pretend that the arbitration mechanism is lower numbered ports are arbitrated first. It doesn't really matter as such, but we'll just select this one as the arbitrated transaction. That read is then looked up in the caches in the interconnect. Again, it's a miss. So we get the little round trip of data. There's a read to the memory, and then there's data returned and allocated into the interconnect's cache. Now, remember that write is sitting there waiting to allocate as well. So the interconnect is going to provide the data back to both of these agents. And as far as agent 0, P0 is concerned, its job is kind of done. It doesn't have any more to do. I have the data, or so I think. But P1 is going to write that entry. Now, that write transaction has been evicted, or perhaps not, but it's being pushed out. Maybe it's a write through cache, and that data value is also being reflected back out to the interconnect. So that data gets allocated into the cache of the interconnect and is written also out to the memory sitting at the bottom of the screen there. So now you have to kind of sit back and think to yourself, okay, so P1 has the latest data because it dirtied it and also reflected it out to memory. But P0 is laboring with a version of the data that's now stale. And wouldn't it be great if, so I'm going to go backwards through this sequence. Wouldn't it be great if at the point that P1 writes this entry, that somehow P0 could find out that actually this data has been sullied in some way, and I'd like to obtain that latest value of that data so that I can work with that rather than the stale information I currently have. So the way we do that, and David mentioned the Moesi protocol, I've got here an example of the Moesi protocol. So why don't we just take a quick look at it? So the way that these protocols are intended to work is they store information about the cache line in a given agent, and also there's a directory of those cache lines kept in the interconnect. And the point of it all is to give ownership of a location to just one of those agents at a given time, but have the ability to have multiple observers actually look at those. So they can make requests to see what the latest data is. They can also make requests to obtain ownership, for example. And in the cases where there's ownership already in a system, and you would require that ownership yourself so you can then work on the entry, then the interconnect has a few things to do. I'm sorry I don't have an animation of kind of one of these snooping sets of transactions, but you can imagine that when you want to obtain permission to own a line, the interconnect has to migrate that ownership from where it currently sits to yourself. And the process kind of goes like this. It will know from its directory which agents have the cache line in flight, which ones are sharing and which ones own it. It'll then make snoops to obtain and invalidate the entries where they are owned. It will then cache that data itself and then make an entry in the requesting, the agent that's requesting ownership, and it will then allocate that line there with potentially the exclusive state. So this state here, the exclusive state, is when an agent holds the exclusive permission to dirty a location, but at the moment it has clean data. It can then move that entry to the modified state once it dirties it, but both are a state of ownership. So for others in the system, there are also is the shared state. Now the shared state is I guess I want to see what the latest version of this is, but I'm not going to own it. So these are quite easy to manage. They don't have write permissions. And then there's the invalid state, where the core can be invalidated if it has dirty data, or it can be invalidated if the line just isn't required anymore. And the whole orchestration of this is down to the interconnect. It determines the states of cache lines within agents by snooping, and it is also involved in the invalidation of cache lines. That's a flavor of kind of what the whole coherency thing is and kind of where it came from. So let's take a look now at our AIP products and take a look at some scenarios. I realize I've got about 5 minutes left here, so I'll try to go as fast as I can through this. So Synopsys provides Assertion IP. That's what we call it. We call it AIPs. They support most of the AMBA protocols, so we've got them for everything from APB up to Chi and latest versions of Chi. They're plug and play, so you just take an example that we deliver to you, and you can use that as a template to bind your design, bind your AIP into your system or your design. All the AIPs are fully configurable via parameters. They're quite easy to set up, and you'll, of course, use these parameters to match the capabilities of your design. You'll be able to configure things like signal bit widths, whether or not certain features are present in your design, protocol features, and of course, different behaviors such as out-of-order transactions, interleaving, and so forth. And the AIP can also be used in both simulation and formal. So it's not just exclusive to formal, you can also use it with VCS, etc. There are, of course, formal optimized versions of the properties as well, and those are enabled when you use formal. And it's kind of designed, to work with the capabilities of the tool. And we would say that, a gold standard for investigating coherency issues with certainly DUTs and also in systems is to try to use formal for bug hunting. So yeah, I mentioned the different sort of usage aspects. You can verify different unit types from, for example, Chi. We can configure the Chi AIP to, for example, work with an RNF dot. You can also configure the Chi AIP to work with subordinates. And it's a similar situation with ACE, so you can configure both subordinate and manager forms of that as well. And not only that, you can also verify interconnects with it. So this is quite important. This case has, I think it's about 8 different AIPs, possibly more, that you can connect around the interconnect ports or interfaces. And it's a one-to-one mapping between AIPs and ports or interfaces. It's different products, again, if you want to track system level coherency. But I'm not talking about that today. And finally, of course, these are useful in your simulation environments so that you are able to monitor each port individually for protocol violations. And yeah, each port, again, is bound with an AIP, and all of the assertions, or all of the properties, rather, in each of those AIPs is turned into an assertion so that all facets can be monitored. Thank you. So yeah, I'm finished with my presentation. Are there any questions?
Thanks, Alex. We've got one question. So can you, I think you've given the example of an interconnect. Can you also use these on NOCs or not, these AIPs?
Yeah, yes, you can. So, I mean, it depends obviously on the protocol that's being used for the NOC. I mean, some people use Coherent Hub Interconnect Chi to build large networks on chip, and that is supported, but it's on a port by port basis. So any large networks, etc., that appear in your system, you only have visibility with the product at the port, but you hope that most protocol violations at the port indicate a larger coherency issue across the system. So although you won't be able to detect the source of the problem, you'll be able to detect that it has occurred at a destination and hopefully then debug those situations.
Got it. Okay, that's great, Alex. We're going to finish here because we've run out of time for your particular talk. But thank you very much, Alex.
Thank you very much. Thank you so much, Mike. Take care.